Hello and welcome back. Today we're going to solve another famous dynamic programming puzzle, and this time is going to be the egg dropping problem. So this one is a little complex, but I will do my best to make it as clear as possible. So the problem is as follows. You are placed in front of a building of n floors, which are labeled from 1 to n, and you are given k eggs. Your mission is to determine the minimum number of egg drops in the worst case in order to determine with certainty the critical floor above which any egg dropped will break. So to better understand the problem, let's see an example. So let's imagine that the building has 7 floors and we are given 3 eggs. We know for sure that one of those floors is the critical floor. So for instance, if that floor was floor number 4, then if we drop the egg from floor number 1, number 2, number 3 or number 4, it will not break. But if we drop it from floor number 5, number 6 or number 7, it will definitely break. So we don't know where the critical floor is. What we actually just want to find is the least number of egg drops that we would need to do in order to determine where that critical floor is in the worst case. So we have several floors to check, and to start we actually need to choose what is the very first floor that we're going to check, and for that we have 7 possibilities. So if you're like me, that you're into sci-fi and time traveling, you can see the first choice as something that is going to create multiple timelines. So here we could decide to start by dropping the egg at floor number 1, number 2, number 3, etc. All these timelines coexist, and what we are actually interested in is to find the one that leads to the minimum number of drops in the worst case. So we will need to check each timeline individually, and that's what we're going to do. Without loss of generality, let's imagine that we decide to first check floor number 5. So we climb the stairs and drop the egg at any windows on the 5th floor. So there are 2 possible results. The egg shatters when it hits the floor, and what we can immediately deduce is that if we drop the egg from any floor above floor number 5, then it will also shatter. So the critical floor is either floor number 1, number 2, number 3 or number 4. And now the situation is as follows. We have dropped 1 egg, and we know that we need to check 4 floors, and we only have 2 eggs remaining. The other result is that the egg does not break when it hits the floor, and what we can immediately deduce is that the critical floor is either floor number 5 or any floor above it. So now the situation is that we have dropped 1 egg, we have 2 floors to check, and we have still 3 eggs. Let's sum up what we have just learned. If the egg shatters when it hits the floor, then the critical floor is strictly below it, and we need to explore a smaller version of the problem, this time with 2 eggs and 4 floors. If the egg does not break when it hits the floor, then the critical floor is either floor number 5 or any floor above it, so now we need to explore a smaller version of the original problem with 3 eggs and 2 floors. So the worst number of egg drops in this timeline is the maximum of the egg drops that we would need to do if the egg shatters and if it doesn't shatter. So it's going to be given by this formula. So we can actually take out the 1 in front of the inner bracket and bring it outside without changing the result. So now that we have seen what would happen if we choose to start with floor number 5, but we still need to explore the other timelines for the first choice. To make it simpler to visualize, we will use this table to track the outcomes. We already know what happened if we start with floor number 5, but if we actually had chosen to start with floor number 1, then the results of the drop would have been, and out of these the worst outcome would have been represented by. So we can actually do the same work for all the other floors, and I will let the animation unfold, but feel free to pause and do the computation on your side and check the result. We end up with this table, and what we are actually interested in is the last column, which tells us the maximum number of egg drops from any floor. Now remember that we want to find the minimum number of egg drops in the worst cases, so we need to find the minimum elements in the last column, and that would actually give us the solution to our problem. So the solution is actually given by this monstrous formula, and again what you can do is move the one in front of the minimum function without changing the result. Okay, now we have a methodology to solve the problem, and what we can try to do is to generalize the recursion formula, and to do so we could redo the computation in the general case, or we can try to spot a pattern. So to spare myself some animation, I will rather go with the second option, but you could redo the computation and you would find the exact same results. So let's examine the recursion formula. What we can notice is that the index, which represents the number of floors that we need to check, is actually going from 0 to 6 on the left side and from 6 to 0 on the right side. Furthermore, the index for the number of eggs that we have only has two values, either 2 or 3. And it actually makes sense because we started with 3 eggs, and if the egg breaks, then we end up with 2 eggs, but if it doesn't break, then we would still have 3 eggs. So now that we have made those observations, we can generalize the recursion formula as follows. And I don't know about you, but it's quite satisfactory to see that this recursion formula would give us a way to compute the result for any value of k and n. And as with any recursion, we would need to add in the base cases, which are actually trivial solutions of the egg dropping problem. And those are actually the following. If we only have one egg, then the strategy to find out the critical floor is to check every floor one by one from bottom to top. And the worst case would be that the critical floor is actually the last floor. So we would need to do n drops. Next, if n is 0, meaning that there is no floor in that building, then we don't need to do any egg drop, so the result is 0. Now let's see how we would code the solution with Python. Here I have defined the function eggDrops, which takes as input the number of eggs and the number of floors to check. First we handle the base case. Then we handle the general case, and since we want to compute the minimum number of egg drops, we start with an arbitrary large value and we explore each floor. And if we find a better alternative, then we update the number of egg drops required. And at the end of the for loop, we have explored all the timelines, and we can return our variable which holds the minimum number of egg drops across all the timelines. Now let's take a look at the time and space complexity of this solution. The time complexity here is exponential, since each recursion is creating 2n problems with decreasing value for k and n. And if we sum them all, then we would get 2 to the n plus k. Now, why n plus k? As I mentioned, k and n have decreasing value, and we know that the recursion is stopping when k equals 1 or n equals 1 or n equals 0. So at most we would need n plus k steps to reach the base cases. For the same reason, the space complexity is a big O of n plus k, because it is the memory allocated by each recursion times the number of steps to reach the base cases. And since we are only creating a variable at each recursion, the overall space complexity is 1 times n plus k. So that's why we have a big O of n plus k for the space complexity. So now if we are taking a coding interview, an exponential time complexity is not at all satisfying, so we need to do better. And to do better in those cases, when we are dealing with dynamic programming, is to introduce a caching mechanism or a memo. That's why we call it memoization. Introducing a cache or a memo pad is actually very efficient, because at some point we're going to make the same computations multiple times, and we can avoid them by simply storing the result that we have already computed. And if we try to solve the same problem more than once, then we can simply take a look at the cache and return the value that is stored there. So we only need to slightly change our logic, and what we're going to do is that first we check that a solution has not already been computed by taking a look at the cache, and if that solution has already been computed, then we simply return the value from the cache. Otherwise we do the same computation as before, but we store the result within the cache before returning it. So after making this improvement, what we're going to see is that the time and space complexity are going to change, and the most interesting thing is that the time complexity is going to go from exponential to polynomial. And this is very interesting because the code is going to be much faster than before, And why do we have actually a big O of n times k? It is that the number of unique problems to solve is actually n times k. So to see it differently, it is actually the number of keys that we would expect to have in the cache. And in this case, it's going to be n times k. And for the space complexity, now we are explicitly using memory to store intermediate results. And what are the number of entries in the cache? It is also n times k. So the space complexity is big O of n times k as well. So that's it for the egg dropping problem. I hope the solution was clear, and if you have any questions, feel free to ask in the comment section and I will answer. If you enjoyed watching the video, please like, comment and subscribe if you want to see more of this. So see you in the next video. Bye!